Okay, so I'm pinch hitting for Paul Messina. He's overseas on another work commitment. And because of that, I'm going to talk about applications. I'm not going to give an ECP. Oh, I'm sorry. Thank you, Doug. Good name, by the way. I'm going to talk, I thought I would give an update on applications, kind of status and progress. I don't think I've briefed this group about apps in particular. I could do that for hours because I'm very excited about what we're doing. So this was hard for me to kind of, select maybe where I'd dive in. And given that we have a manufacturing theme here and machine learning theme, materials theme, I'm going to choose maybe 2 or 3 to try to take you through, how the teams are doing. So I am going to focus on just the application development area, which is the area that I lead on behalf of ECP. So if we go back about a year, we selected 22 application projects in sort of September 2016. So they've been executing. These are teams of anywhere from 5 to 15 or 20, depending on how much of the team is participating actively or not. But and that's augmented, of course, by our national security application. So there's another 3 there. So we have 25 total in our portfolio that have been executing for about a year. So we're starting to get a pretty good sense of what the teams are doing. We're pushing them pretty hard with a sense of urgency, milestone-based approach. And for the most part, we're very happy with what we're seeing. We just went through reviewing all the projects, and I'll sort of reflect on that a little bit later. But just kind of back up, there are many, many scope considerations and constraints when you're choosing these applications. Ideally, well, not ideally, but it's not up to me. All I basically do is work with the teams and recommend the DOE. These look really good, and you see all the different types of considerations. Mission need is very important. All of our application teams need to be targeting a high priority, what I'll call a challenge problem. But because we want to emit a more general ecosystem, we need to make sure we're covering motifs and we're covering a software stack, in particular look at data analytics. I think we'd be cheating if we went for all low-risk endeavors. So we want to have a mix of risks, high risk, high return applications. We're interested in non-traditional applications as well, and I'll maybe define what that means. So this went into our selections about a year ago. Not easy selections, by the way. And so here's kind of the eye chart of the applications, and the ones in green are the ones, time permitting, that I will try to cover. And I see I have this stopwatch here, so I better keep moving. But we put these applications in various bins, okay? And I made these bins, and you could probably look at them and come up with different ones. But we have a very nice portfolio that covers a broad spectrum, which essentially answers to the ECP mission need, namely that we develop applications ready on day one at Exascale to cover the broad DOE mission portfolio as well as other agencies. So if depending on how you count program offices, that's about a dozen program offices. So we interacted a lot with the program offices in science, energy, and NSA in trying to target these challenge problems, and I'll define what that means. So you see we have a very rich portfolio, and some you'll recognize, maybe a lot of them in terms of the teams and the codes and the PIs. There's only so many good computer and computational scientists, so in a lot of cases we are really helping to push a team that's really petascale mature, already delivering to that kind of next step, okay? So with regard to, and this is an eye chart, but I sat down with each one of the apps teams and we said, you're doing great things at petascale, but what are the gaps? And you can think of a gap here as, inability to reduce uncertainties or generate a high confidence result or explore a new area of physics. And so for each one of the projects, the bullets on the right really represents kind of what status quo means if we can't fill that gap. And not surprisingly, from a predictivity point of view for simulation and data analytics as well, you have certain gaps that are fairly, not surprising and fairly common. You're simplifying, or you have simplified or incomplete physics even at petascale. Simulation detail is insufficient. Here, think of time and length scale resolutions, or ability to do long time scales. You can only simulate a subset of scenarios of interest. This is very important when you're talking about coupled multi-physics or ensembles to get good statistics. Uncertainty insufficiently quantified. For the most part, that's true of almost all applications. It's really hard to get a good handle on what are our uncertainties, and can we actually quantify them? That's very important, not just to make decisions for applications, consequential decisions as a result of the simulations, but it also tells you where you should put your resources to continue to improve the application. So knowing your uncertainties is very important and also very difficult. Unable to intersect the design cycle, this has to do with time from concept to solution. Many times mod sim or, and in particular, just can't generate an answer quick enough to impact ultimately the human decision. And with data analytics, we're really seeing that we're not doing very well with our data. We're not analyzing it adequately or quickly enough, or we're essentially throwing away a lot of the data or losing the opportunity to discover knowledge. So we believe there's a lot of gaps that Exascale can fill. There'll be a lot more to do after Exascale because as apps people, we always can consume whatever's out there. But we got a nice sort of summary of where the gaps are for each app and how Exascale might help to fill it. So one of the things we've been asked is just, what are metrics for applications? What constitutes success? And this is kind of a gray area. It's really squishy, but this is sort of Doug's view of app metrics. We want to be able to deliver improved and impactful science and engineering, and let's just call that performance. And perhaps it's, as an apps person, I don't call better science performance, but let's just say that we tend to use it that way. And again, something that represents a step change in a problem of national importance is probably a better way to state it. As performance portable as possible and reasonable, apps people still really want to run everywhere they can. That said, performance portability is very important. I think it's a journey, not a destination. It's very difficult, but portability. And we don't want boutique one-off applications. So ideally, most application developers won't go down a rat hole just to run really well on one system. There are certain cases from a mission point of view that make sense, but generally we don't want boutique one-off applications. Want to make effective use of the capable system, really ready to roll on the system on day one, certainly related to the other two. More and more we're seeing agile software project management, which I think, from what I can tell, started more in the commercial world, infused into R&D, and I think it has it's been very effective for us. And there I think it's not only the methodology about how you go about developing software, but you want your software to be agile. Okay, my view is an application may be traditional mod sim. It ought to roll on and say, oh, well, this looks like a machine learning node. I think I know how to use this, instead of just tailoring ourselves to one sort of hardware. And high priority. Somebody has to really care about these results, at least in ECP, other than the app people who always care. So how can we be impactful? Well, we're asking the teams to target specific challenge problems. I'm not calling them grand challenge because I don't think we ever get there with grand challenges. But and this is really focusing the development, and it allows us to measure their progress. So basically, a challenge problem, I'll skip to the end, is one has a solution supposedly amenable to mod sim and/or data analytic computing. It's currently intractable on today's hardware. It requires, in sort of a rigorous way, exascale resources, whether it be throughput, memory, etc. And it matters to somebody. It's a high priority problem. And so each one of the apps teams, when we negotiated with them, has one or more, not many, specific challenge problems. The expectation here, and we have to be careful, is that the application software technology will still be more general. So we want to make sure we have focused development, but yet expect to have a more general capability. Okay, let's see. So delivering on the challenge problem. The way we're viewing this is, as time goes on, the challenge problem will have more quantity, will be more quantified. For example, like our quantum material science code, Paul Ken at Oak Ridge is targeting 1,056 nickel oxide atoms. Very particular problem. Wants to get 50 threads per walker. Has really laid out almost scarily too much in detail, but we anticipate that'll get more quantitative as we move forward, okay? And we since kind of this first year had a first run with the teams in terms of defining their challenge problems with a little more of a metric. And that's important for us as well as DOE to measure progress. At a high level, let's just view this better science as work rate, higher work rate. In other words, work could be you're doing more physics, so W can go up, or you're getting faster turnaround, T can go down. But in general, we're interested in work rate, not work, not time, but work rate. And so what we're interested in is measuring the work rate relative to today. So if you hear something like 50x performance, it's really kind of this multiplier on work rate. And we work with each of the apps team to essentially define what your work rate is. It might be number of Monte Carlo particles pushed per second. It might be a number of atoms, in a scaled way. So we've worked pretty hard to make sure that the work rate really scales, really maps back to the science, okay? It's just not peak flops or whatever. Also, every challenge problem is very specific. It's rare to see something pretty generic that works from one app to the other. So each of the apps teams has a document and essentially, a short briefing on what their specific challenge problem is and how they're going to define success. But in the end, what does that mean? In the end game is predictivity. We want to reduce our uncertainties. I like the NRC, Nuclear Regulatory Commission definition of 95-95, which is a 95% chance the simulation will match 95% of the real world data. To me, in the end, it's matching reality. And really, this is kind of right now somewhat beyond the scope of ECP, which is being able to really nail down UQ and do lots of ensembles. That's very important. And typically, those sorts of resources can be 10x the development when you get in the hands of early users to really hammer these things out. So there's still more work to do, but the point is the supposition is work rate going up will be synonymous, it ought to be, with UQ going down, okay? So portability, we did ask the teams, when I've been asked, what does portability mean? Well, it's really different for every app team. So it's important that we have the teams be as portable as possible, and we came up with these 4 dimensions, and every application team is essentially defined what they think is reasonable. So the first is you can't cheat and run a problem that doesn't matter. You have to run a real problem and get the right answer. And I don't think it necessarily needs to be 64-bit comparison, okay? So we want to have a relevant science problem achieve the correct result, not surprising. We like the rate of performance to not vary excessively from platform to platform, and there's where we're kind of all over the map. It might be, some people might go, I think it's 2x, or I think it's 50%, or I think it's even higher. This is probably the one that's most difficult to define. And it's not that this will have a very specific target, but it's important to think about this relative performance and understand why you're seeing differences. So we've asked the teams to sort of speculate what, say 2 exascale systems, what they might see in some sort of normalized fashion. In my view, you can't cheat an if-def 2 codes together and call that portable, okay? So the breadth and depth of changes are needed for certain kernels, okay? But we don't want to essentially carry 2 code bases along, ideally, okay? And if a new machine shows up and, who knows what they'll look like, it shouldn't take years to port. I mean, we'd like to think it takes weeks or months max, okay? And so these are tough, open-ended questions, but we're asking the teams to really think more about what's a portability metric, because we don't have a specific metric. It's much more difficult to work towards something. So in terms of risk and challenges, this is sort of Doug's view of what I see, and I don't think you're going to see anything here very surprising. We've got on-node memory and compute hierarchies. Application people are very concerned about choosing a data structure that might work for one hardware and not another, and not having their software architecture sort of agile enough to accommodate multiple data structures. In other words, they can be kind of infusive throughout the code. So that's leading us to, I call it kind of back to the future, where we're moving more back toward frameworks or kind of memory management models, components that sort of sit underneath the apps that allow application people to essentially say, I'm on a KNL or I got a GPU, give me an array back. And was popular in the 80s and 90s, and there's some risk there because you hand over some control of what you're doing to some smart computer scientists that hopefully will stick around. But we're seeing a lot of the teams move kind of back toward that paradigm in terms of their development. what to use where and how on programming models, in particular task-based runtime systems. Not only that, but a later bullet here sort of points out if I call a linear solver library, previous speakers talking about PETSI, for example, it might have its own task-based model as well as mine. I might be using HPX or solver might be using parsec, and we're going to get thread, contention, and collision. So we have to be able to, orchestrate these between our various libraries, and not being developed independently is going to create problems. You can kind of read these. I don't have time to go through all of them. I will just say that let me jump to the last one, staffing. Right now on the teams we have I think some of the best and brightest computer and computational scientists in the community, senior people who've done this before, really engage as leaders. But we've also got a lot of really good early career people that are very excited to be a part of this. So far, the recruitment aspect hasn't been a challenge. I think it's the retention is going to be a challenge, meaning these folks are being trained up to work, on the coolest systems with the latest software technologies, and so they're very marketable. So this is certainly a risk for us moving forward, is sort of making sure we keep our claws into these people that are doing great stuff. So a little bit about this convergence. Now I know it's been talked about previous sessions here, but we are seeing this in ECP, and we probably have our list of 22, 3 or 4 more card-carrying data analytics apps, but the rest are more traditional mod sim, where they're really starting to infuse data analytics as part of their workflow. And I don't think anybody disagree that the data analytic computing or AI is finding they're facing barriers to scalability. We've seen this with some of the industry machine learning frameworks, and physics-informed machine learning is starting to become very interesting in an improved way, as opposed to, say, linear regression, is to use some physics constraints in the fit. At the same time, mod sim, we're demanding a more dynamic interaction between analysis and simulations, and so we're really seeing these two come together. And from the point of view of the application portfolio, I sat down and I kind of categorized our application scope here. And I see workflows that either are being used or are needed, as cited by the PIs, that bring these two things together. And I have a broad definition of in situ analytics. I'm going to call that upstream, during, and downstream. But you can see examples in the italicized parentheses are basically the project. Some have been doing analytics like halo finding and cosmology, looking for certain vortical structures in our ocean and climate, which is certainly of interest now with Irma. Trying to understand what turbulent plasma structures look like. So we've seen this for a while, but the teams are bringing in, I think, more kind of production-hardened machine learning capabilities as part of the workflow. I think we're going to see more in computational steering. And I'm not going to have time to cover the precision medicine for cancer or candle application. If Rick Stevens from Argonne hasn't come to this group and spoke, it would be good to get him to dive into that. But in this case, they're driving ensembles of electrodynamic simulations with machine learning, and they're looking for particular aspects of the RAS protein and the clustering, and to help them make choices about the next set of simulations. Lawrence Livermore has some interesting work going on in shock physics, where the mesh is following the compressible and shock flow. And traditionally, humans have intervened and said, "Well, that mesh looks bad. I better restart and fix it by hand." Well, now you can essentially assign a quality metric to the mesh, and the machine learning algorithm can do that for you. Essentially, automate some of these things that humans don't necessarily have to be involved in anymore. Also, modeling unresolved physics. If you look at the literature, there's a lot of interesting turbulence modeling work going on the fly. Data analytics for choosing turbulence parameters. That's sort of a natural. And on the climate side, superparameterization for subgrid cloud models is also another candidate. So we are seeing some of that. What I'll call predictive analytics, or the machine learning or the AI app, is at the top of the pyramid. That's our cancer application. and CANDLE, Cancer Distributed Learning Environment. It's jointly with NIH and NCI, as well as 4 national labs and several universities. There, what Rick Stevens and his team are doing, they're building, I like their approach. They're building an environment that's bringing in all the kind of standard industry frameworks towards Tiano, TensorFlow, Caffe, et cetera, making sure they can interop using things like Swift and Keras to glue them together, and essentially pounding those things out on these cancer problems to understand, just where do they work well and where do they don't, where do we need to do more work to scale. And so start with some of these great industry frameworks and then see how you need to move forward. I see I just have a couple of minutes together to go, so I had several examples. I'm going to jump to the end with a few concluding remarks. Actually, there's a great additive manufacturing application I didn't get to, but it ties in really well with what Lori said. This group is looking at, let me say, sort of the entire sort of end-to-end workflow in terms of the physics and the scales, from microstructure to mesoscale to continuum, and really, really complicated problem. It's a great plan, and they're bringing together, multiple community and DOE codes, ultimately to emit an exascale environment for, for metal alloy manufacturing. So I didn't want to omit that one. Okay, so over time, just some comments. How are applications valued by the community? Well, for me, at the top of the list is they've been verified and validated, so the results come with high confidence. One might be able to equate that with kind of the number of tests. How many tests the applications? The breadth and depth of testing is very important. They have to be usable, portable without major hits. I mentioned extensible, accessible, and frankly, genealogy means something in this community. Okay, what team and who matters. And there's always new people that come onto the block, which is great, but genealogy matters as well. So let me just conclude with the apps teams. This is obviously a subjective opinion on my part because I'm near and dear to them. After a year, I think they're off to a great start. We have them running in a fairly projectized mode. They have multiple milestones per year, each team. We're requiring, say, a release, a demonstration simulation, documented work on any algorithms, models, or software redesign. And so each team typically has kind of 2 to 6 milestones. Like I said, we've really worked with them to define as specific as we can science-based challenge problems, albeit with some flexibility required for R&D that map to 2 figures of merit, so we can really have specific targets and track them. And we just put them through an annual review last month, and all the teams are really doing very well, considering where they've started. I'm excited about where we're headed. It's going to be a tough run. We're going to move fast with a very sense of urgency. But from what I can tell, we're lucky to have a great set of teams that are all in on really trying to get ready for exascale. So that said, I wore out my welcome, so I better stop here. Thank you.
We have some questions for Doug.
I've got the evolution versus revolution question. This morning we heard that the old thought a while ago was that there was going to have to be a big revolution in programming style and approach, but now it's more evolution. So do you agree with that? And if you do, then what did we have wrong then? What's changed since then?
Well, as an apps developer for 35 years, I loved to just get on new machines I couldn't run on, and I didn't view that as an evolution. It was probably, it's a revolution, probably more evolution. So I'm a little tainted, a little influenced by my own experience. But I would say almost every app has a combination thereof. In other words, they're evolving some existing algorithms or models kind of as path, plan A. And plan B, they're doing a little more surgical insertion. An example is, I'm going to try my runtime system down here in this kernel instead of going, MPI OpenMP, okay? We really need to make sure that the applications, deliver science. And so, in general, people aren't taking direct right turns, okay? We're looking at where we can, get more bang for the buck in a more And again, I'm going to say a more of a revolutionary approach is a totally changed programming model, but in fact, it's also a new science model, okay? As an example, one of the apps I didn't get to show, but I'll mention too, is led by our voter Los Alamos, and he's coupled lamps, an MD code for more for metals, with the DFT code running real time. So basically, quantum code handing potentials back to lamps real time. That's potentially revolutionary. From a computer science point of view, not so much. You're orchestrating, lots of simulations, but from a science point of view, it's potentially revolutionary. So I think each app has both. The last thing I'll say, if there's a few teams that are, I would say, kind of sandbagging and taking the easy approach, and there we're putting milestones in. No, you've got to try this. So we're having to force the integration, which I think makes sense. So we're trying to be pushy where we can. So.
Hey Doug, thanks for the talk. So I have a comment. So what I see as revolutionary is actually that there is no longer a requirement to run one coherent code on the whole flat machine that's on the exascale. That is revolutionary. If that's true, why not buy 1,000 petascale machines?
1,000 petascale machines are very, very useful and important to do science, okay? Every one of these teams has a spectrum of simulations they need to do that could be served in part by ensembles, okay? Independent ensembles, yeah, you don't need an exascale system, but ensembles, for example, parallel replica dynamics for MD, there where you need to have your ensembles orchestrated on one system to make choices about moving forward is a little different. My point about UQ is probably more well served for sort of 1,000 petaflop machines as opposed to one large integrated system. I would argue that it's the challenge problems that we've chosen need an integrated system, okay, and have very specific figures of merit related to that, okay. But a key part of every one of those challenge problems is being able to do statistical analysis and ensembles. So, I think it'd be great if we had both, I guess is the way to say it. So.
Any other questions? Okay, Doug, thank you very much.
Thank you.